Good morning, student. Let's start today's class. Today we are going to discuss about aerodynamics of the rotor blade. Okay, the wind. In previous classes we have studied about the history of wind wind energy converter. Okay, in this converter we have seen that there are windmill are there. Okay, and in the windmill there are several blades are there. Okay, in the rotors blades are there. So for high efficiency, now let us see the aerodynamics of the rotor blade. Okay, to get the efficiency more and more from that rotor should be dynamic, so that it produce uh, high energy. Okay, now in the aerodynamic of the rotor blade, first one is wind stream profile. Okay, wind stream first one is how what let us know that about wind stream profile. What is wind stream profile? Okay, a high value of the power coefficient is possible though an optimum aerodynamic design of the rotor blade. Okay, so the power coefficient is higher, okay, if the aerodynamic design of the rotor blade is good. Okay, in order to understand the basic process, the one should consider the airstream, okay, profile, which are used for the aerofoil, okay, of the aeroplane, and for the for the shovels in turbo machines. Okay, figure 11 to 8, this figure, okay, shows such a profile with the pressure distribution along along the length of the profile. Okay, this figure shows the profile, okay, wind profile. Due to the convexity, okay, of the profile, due to the convexity means this is the convex. Okay, this is the 1 minute, this is the convex. Okay, and due to that convexity, okay, of the profile, the upper side facing the window, okay, facing the wind. Okay, uh, a displacement effect takes place. Okay, the air stream come closer to each other. Here you see the air stream, this line is representing air stream. Okay, and then the air streams comes closer in the upper side. Okay, closer to each other, which essentially mean that the wind velocity of the upper side, okay, of the profile is higher than the approach velocity. Here you see, here what happened, due to the this convexity profile, here the stream is closer to each other. Okay, all streams is closer to each other. So due to this stream is closer to each other, okay, here what happened, the pressure and this represented here the low pressure created. Okay, in the upper side the low pressure create, and one vacuum like situation created in the upper side, and similarly in the downside. Okay, this concave due to the concavity, okay, this wind profile or a wind stream get wider and wider. Okay, so here the high pressure created, okay, in the downside high pressure created. So due to that pressure difference, okay, that means here high pressure, here low pressure created. So one lift force or one uh, force of lift is created in the profile or uh, in the profile. Okay, so here on this side, and here you see something over pressure, this parallel effect of partial vacuum on the upper side of the profile and over pressure on the lower side of the profile result in the creation of a buoyancy force. Okay, that is called buoyancy force. That the lifting force is called buoyancy force. Okay, now you see here, this is PS. PS means static atomic pressure, atmospheric pressure. This is constant. So when the due to the 1 minute, when due to this is the atmospheric pressure, and it increases due to the convexity. Okay, from in up to the S point. Okay, or the due to the facing of the profile. Okay, in the direction of the flow, this pressure increases. Okay, now when this pressure increases up to PG, the velocity head. Okay, the PG. Okay, then after in S. Okay, this is for upward. Okay, upward side profile, upward side. Okay, due to this pressure decreases, due to here also it represents the pressure decreases up to H, this point. Okay, up to H. Okay, and in the at that time, okay, the pressure increases in the downward side. This pressure increases slightly, increases downward side. Okay, sorry, slightly decreases downward side, but not like the upward side. Okay, the in the H side, the pressure increases and get constant as a PS. Okay, here also PS, mean atmospheric pressure constant. Okay, so this pressure variation is happened like this. Okay, now now you see this is the for the lift force. Okay, the force which is placed in the profile, or due to the pressure variation, the lift force in the profile, one can write this formula. Remember this formula. Okay, now here Fa is called lift force. Okay, PL is called pressure at the lower side of the profile. Okay, then Pu is the pressure on the upper side of the profile. Okay, L is the length, that means length of profile, and Bp is the width of the profile. Okay, this is the length of the profile, this is Bp. Okay, and this is width. Okay, that much. That means if the profile is like that, like this, sorry, like this. Okay, 1 minute. This is the profile, and like this profile. Okay, this is the profile, let's say. So this is the width, this is the length of the profile, or that is, this is the Bp, and this width is what? Length is L, and width is the profile is Bp. Okay, now let us see what is let us see buoyancy coefficient or drag coefficient. Okay, now if the profile in the direction of the flow is not as symmetric as shown in figure 11.1, like this, symmetric means what? This is the parallel to the flow of, or the profile is parallel to the flow of uh, uh, flow of uh, flow of air. Okay, or flow of wind. Okay, if that is not the case, let's say here you see the flow of this. Okay, the flow of wind is like this. Okay, but the profile is like this, that is not parallel to the flow of wind. So whenever this happened, okay, that two force work on the system. Okay, two force work on the in the profile. Okay, one is lift force Fa, this one perpendicular to the direction of the flow. Okay, wind flow, perpendicular to the wind flow, and one is Fr. This means drag force. Okay, parallel to the direction of the flow. These two force created, okay, due to the profile is not symmetric with the flow of wind. Okay, now, and the angle alpha A, this angle, this angle, that means this angle, okay, this angle alpha a between the plane of the profile and the flow direction is called the angle of attract, angle of attract or or inclined angle. Okay, the drag force Fr, which is caused at the surface of the profile due to the air friction. Okay, this Fr, air friction, can calculated from the following formula. Okay, this is the formula for drag force, which is created for the friction of the profile with the air, flow of air. Now here you see Fr is the drag force of the profile, Cr is the drag coefficient. Okay, this Cr, then alpha, and then alpha a, then gamma a, not gamma a, this is rho a, air density. Okay, now W is the apparent wind velocity. Okay, A is the profile area. Okay, now for the profile area, A can be written as A is LB. You know, the profile is a rectangular. Okay, so in the area is width into length. Okay, the width is BP and length is L. Okay, now place this A in the analogy with the expression of the drag force Fr. The force F due to the lift can be written as Fa is, okay, this Fa, that means lift force, okay, is, the formula is this. Okay, now the resultant force of the profile is given by the vector sum of the lift force Fa and the drag force Fr. That means this is the resultant force, this is FRS, this is the resultant force. You know, when there is a two components of the force, then from that when we get one component, we take the resultant force. Okay, and this resultant force is calculated by vector sum of these two force. Okay, then the drag coefficient Cr and the lift coefficient Ca are determined experimentally for a particular profile. Okay, they are represented on a polar diagram. Okay, in with the angle of attack as a permanent. Figure 11.12 shows shows such a diagram. The diagram show that up to a certain negative value of alpha a, Ca is positive from this Ca is positive for from negative 0 degree to plus 15 degree. Okay, for large value it decreases again. Okay, the ratio of Ca and Cr is also used for characterize the aerodynamic profile. Okay, the ratio of Ca and Cr is also known as the lift to drag ratio, represented by Eg. Okay, this is the aerodynamic profile represented. Okay, this optimal value of Eg is obtained by tangent to the origin of the polar diagram. Okay, then the diagram give the this figure 12 11.12 correspond to the uh, so here let's finish this class. Okay, this figure 11.12 we include I include in the next class, and we discuss this concept after seeing this figure. Okay, thank you.